All right, we're on the tail end of things now. I've got two more examples for you. So now we have, you can probably start this by yourself, but if you want to, if you want to pause the video and start, that's fine. I'm going to set up the same way how to calculate with ice the concentration of a species that will control the pH. So let's figure out what species is coming from ammonium chloride in significant amounts. Let's predict the pH first, though, based off the parent acid and parent base. So this is coming from ammonia or ammonium hydroxide. I'll write it as ammonium hydroxide for you, just so you can see the hydroxide here. And then this is coming from hydrochloric acid, only one of which is strong, so this strong acid is going to supersede the weak base that is here, so this should yield an acidic solution. And that's just there for you to check later on that everything was calculated correctly. The ammonium ion and the chloride ion can interact with water, and you'll notice that the chloride ion, which is coming from a strong acid, is going to be a very, very weak conjugate base. So weak conjugate base means that, yeah, it could accept an H+, but in forming of hydrochloric acid, we know it's going to have that 100% ionization back towards the reactant, so we call this a no reaction. The ammonium chloride is the part that's more important. I actually need some space here, so I'm going to rewrite this. Oops. So ammonium plus water is going to be a great conjugate acid. So I'm going to put strong conjugate acid here to remind you of that. And so it will protonate water, so it's actually the stronger acid of the two. And it will protonate water to yield ammonia and hydronium. And so then you're like, aha, it's making hydronium, it's going to be acidic. So that's another double win for us so far. And if you're thinking about how ammonium is acting, it's acting as an acid. So then you're assuming that there's a Ka associated with this BCE. We don't have a Ka though. We have, for ammonia, the Kb of ammonia is 1.8 times 10 to the negative fifth. You might actually start to memorize these, some of them, because we use them quite a bit. So we always know the Kw again, so then to find the Ka of ammonium, the conjugate acid of ammonia, you're going to do Kw divided by Kb, so that's 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth. The Ka value of ammonia acting as an acid is 5.55 times 10 to the negative 10th. So that value is going to be used for our setup of the expression here in just a second. The concentration given is 0.01 molar. So 0.01 molar minus x. X and x are created, so this gets to be redundant. We probably can start shortening our work a little bit here. So setting up the Ka expression in your head, ammonium, which is x, times hydronium, which is x, gives us x squared over 0.010 minus x. So minusing x is probably going to be insignificant, so give us a value that's going to be negligible. And oops, if you check your work afterwards, you'll see that, but we do have a very, very low value, and so that when we find x, it's going to probably be insignificant. So don't always assume, but on some of these you'll start to see the differences. So x is going to be equal to 0.01 times 5.55 times 10 to the negative 10th, square root of that, and that's 2.36 times 10 to the negative 6th molar, and then your job is to say, what the heck is x? Well, that happens to be hydronium, and that's our species of interest to give us the ability to calculate pH. So hydronium being 10 to the negative 6, you're probably thinking, all right, pH is going to be maxed out at 6, so let's call it a 5.7 or something like that. So calculated, actually, pH is the negative log of 2.36 times 10 to the negative 6. That's a 5.63 pH. So it is between the 5 and 6 region, so that's great because it's definitely double or maybe quadruply determining that it is acidic and is a weak acid. So you've seen all the combinations so far. The one we've yet to consider is the combination of I'm going to skip that for now, the combination of a weak and weak, and let's verify that real fast. Ammonium comes from ammonium hydroxide or ammonia, which is a weak base, and acetate comes from acetic acid, which is a weak acid. So since neither is stronger, we cannot just assume what the pH is. This is where you must consider Ka value versus the Kb value for the ions. And from there, whoever is bigger will determine the pH. And it's just acidic, basic, or neutral, and there's no numerical value for this one. So let's write out the dissociations as they would react with water. Ammonium reacting with water equilibrates to ammonia. And you can see the protonation of water from this conjugate acid, which is a strong conjugate acid. So protonation of water makes hydronium. And so since it's acting as an acid, I have to find the Ka for that. We actually just did this one, so I'll just set up the numerical kind of calculation. Kw over Kb for ammonia. And that was 1.8 times 10 to the negative, oops, that's actually a lie, that was 5.56 times 10 to the negative 10, because it was Kw divided by the Kb value, and Kb value for ammonia is 1.8 times 10 to the negative 5th. The second dissociation, all right, a little small down here, is acetate. Acetate reacting with water serves as a great base because it can accept a proton back. So in this case, it's the conjugate base. It dissociates, equilibrates to acetic acid, and water is left without an H, giving us hydroxide. The Kb value for acetate in water is going to be stemming from the Ka value for acetate. And I'm going to actually need a little space here. So the Kb value for that is coming from Kw over Ka for acetic acid. We have actually used the Ka for acetic acid before, and so I'll write it up here for you, but 10 to the negative 14th divided by the Ka for acetic, guess what is 1.8 times 10 to the negative 5th? And when we do that math, you're going to see that you're going to see that the K values are the same. So Kb, when you divide, is 5.56 times 10 to the negative 10. That's very rare to see, but in this case we do. We see the Kb for acetate and the Ka for ammonium to be the same. So in this case, Ka and Kb are equal, so it is a neutral salt, simply because their strength of dissociation or reacting with water is going to yield same amounts of hydroxide and hydroniums, just based off how these two reactions are occurring at the same level of ionization. If the Ka was greater, the salt would be acidic, and if the Kb was bigger, the salt in water would be basic. So that was the grand finale there. There's a salt hydrolysis problem set you should jump on. We are actually going to be doing a pH and salt hydrolysis lab tomorrow, where you will be practicing this some more, so you'll have quite a bit of practice, and you'll get very comfortable with the introduction to acid-base equilibrium. There's some more prediction of acidity levels of salts if you need it, and then this is the final question or introduction part to your notes. This is a reaction of hexaqualuminate, and it just shows how this complex ion, which we actually referenced a while back, how it takes one of the waters and it allows for it to react, and it donates a proton to to water to yield hydronium. So this is showing how like a weird ion, a complex ion, can actually still be acidic, basic, or neutral in solution based on how it can interact with water. So you'll see that delivery of the proton to yield just 5 waters inside versus 6, and 1 hydroxide, and then the 1 hydronium made over here, showing us that it is an acidic salt or an acidic ion. So that's kind of a weird example, but that's just one part of the notes that I wanted to make sure we got to. All right, have fun with your prop set.